Today we have one of the preeminent minds in Oracle database security, or heck, any database security for that reason. David Litchfield, presenting Hacking and Forensicating an Oracle database server. And without further ado, here's Mr. Litchfield.
Good afternoon, first and foremost. Welcome to Las Vegas. Well, actually, you've been here for a couple of days already, so the welcome is probably everyone's dying to get home, so I'll probably greet you with a goodbye. Yeah, this is the final talk of the day. It's going to be a presentation, obviously, about hacking and doing a forensics investigation on an Oracle database server. It's work I've been doing on and off for about the past 3-4 years. I sold my company a few years ago, so I've had an extended holiday, and I get sidetracked with diving, and then every so often I come back to the programming and researching and everything like that. So this is basically the culmination of about 3 to 4 years worth of research interspersed with some diving. So who am I? Many of you in here probably don't know who I am, so I better quickly introduce myself. I'm a vulnerability researcher by nature and trade. I started out in buffer overflow exploitation, but I seem to be remembered for my work in the database security arena mostly. As a consequence of doing a lot of attack C&E-based work on database servers, it sort of led on to the forensic side of things, because no one seems to be doing that, or at the time anyway, when I started this research. So I have a company now which essentially exists as a vessel to hold free software. I'm developing, everything presented today is free in terms of the tools and the papers and everything like that. So I'm not here to sell you anything, so you can breathe normally. And so prior to Verity, I set up NGS software, worked for AtStake prior to that, and Cerberus and Arca Inc., which was a wholly owned subsidiary of Exodus Communications. I've written a couple of books on database security, namely the Oracle Hacker's Handbook, the Database Hacker's Handbook, and a couple of other books on things like shellcoders and so on. If you want to follow me and my research, I can be found on Twitter at @dlitchfield, or if you want to email me, like any questions or anything like that, my email address is david@verity with a 3 for an E, .com. Okay, so the what and the why. So database breaches happen all the time. I mean, that's undeniable. And there seems to be very, very database-specific forensics tools out there, which I find shocking. The common approach these days, it seems to be looking at using grep to try and parse database log files. Now, given that most of the files that contain the evidence are binary in nature, grep really doesn't help us very much, and it doesn't understand the structure and so on. In fact, I sent out an email a few months ago to the Oracle L mailing list, which is basically a list for Oracle DBAs and programmers and so on, asking them, you know, who checks their logs and how often they check their logs, and if they are checking their logs, what tools are they using? And only 1/3 of DBAs are actually checking their logs, which I find, as a statistic, quite astonishing. It's not the most scientifically robust research, of course, but it gives us a good idea of, a good sample of Oracle DBAs out there and how many are actually checking their logs. So approximately 1/3. Now, in terms of the whole database forensics angle, there seems to be this no man's land where no one's doing the work in database forensics, simply because I think it's the incident response people understand very well certain technologies and concentrate on those, whereas when it gets to database servers, you have to understand things like SQL, you have to understand the architecture, and there's a whole lot of extra. Essentially, to become a database forensics expert, it's not simply good enough to be a forensics guy. You have to understand databases entirely as well. And so there's probably too much information there. So the incident response guys and the forensics guys probably leave it to the database guys to worry about the whole investigation side. Whereas the database guys are probably thinking, well, I know really everything I know about database servers, but the whole forensic side is way out of my depth and comfort zone, so I'll leave that to the IR guys. So that no one seems to be doing anything in this area. Yeah, as it currently stands, there are no commercially available database-specific forensic tools available that analyze data to the depth it can be analyzed and extraction of evidence and so on. There are a couple of free tools, but as far as I'm aware, I'm the only one who's providing the free tools. So all the tools that are out there at the moment are my tools, essentially, unless something has changed and I just haven't found out about it. So, compromising the database. We're going to split this talk into two. One is looking at how attackers compromise Oracle database servers. And the second half is looking at what evidence is left behind after a compromise. So a typical attack comprises of several stages. First off, the attacker needs to gain access. Now, how that happens depends obviously on where the attacker exists on the network. Are they external to the network, like out on the internet, or are they internal to the network with already high privileges and so on? So gaining access could be through piggybacking on SQL injection, for example, in terms of an attacker on the internet coming through a web application and attempting to gain access to the database that way. If someone can gain direct access to the database server, they can start to begin to exploit flaws that don't require user IDs and passwords. For example, buffer overflows in the TNS listener and in older versions of Oracle exploiting things like external procedures, which we'll come to in a minute. So once they've gained access, and we'll look into that deeper in a few minutes, the next thing they'll try and do is obviously elevate their privileges. So let's say they get in as a lowly privileged account that only has create session privileges. That means, that's all they can do is connect to the database server. From there, they obviously want to do more to the database server. They want to be able to gain access to privileged information. They might want to shell out to the operating system or gain further access to the network. So that requires elevating privileges. And there's a number of well-documented ways in which attackers can go around elevating their privileges. Once they've got the privileges they require to effect their attack, obviously they might want to modify data, they might want to delete data, or they might want to simply exfiltrate data. And another common event that happens with database compromise is, of course, attempting to break out of the database server. Now that might mean just gaining access to the underlying host operating system, or it might be extending further into the network and using the Oracle database server as a staging platform. So we'll look at all of these sections individually. So, and with forensics in mind, of course. So in many attacks, in many situations rather, there are attacks that require no user ID and password. Now, this is obviously, might be a shocking news to some people, it might not be shocking news to other people. Given that Oracle is an EAL4 plus certified product, in other words, under the common criteria, one would think that you should not be able to gain access so trivially to an Oracle database server without a user ID and password. But over the years, there have been multiple vulnerabilities that allow an attacker to gain access without a user ID and password. So to name but a few, there's TNS listener buffer overflows. So the TNS listener is a wee bit of software that sits in front of the Oracle database server, essentially. And when a client connects, the TNS listener is the one that hands off connections to the Oracle process and so on. And it's got a large attack surface itself. And one of the funniest and most ironic vulnerabilities that Oracle suffered from in the past was an overly long username buffer overflow. So if you presented a username which was longer than the buffer that was set aside to contain the username, the buffer would overflow and you could gain, you could execute code remotely as the user running the Oracle process. So on Windows, that would be local system. And on Unix variants, it would be the Oracle user. Now, obviously, if you're running code as Oracle or local system, you are God as far as that database is concerned. Now, Oracle fixed that, and over time, there were other overly long username overflows in the XML database, for example. So, earlier versions of Oracle, like in Oracle 9 and 10, they had the XML database that listened on TCP port 2100 for FTP connections, and port 8080 for HTTP connections. And again, an overly long username and password would overflow stack-based buffers and heap-based buffers in certain cases, and allow an attacker to compromise the database server and execute arbitrary code. Another fun one is external procedures. So within the Oracle database server itself, there are things known as PLSQL procedures, okay? And if PLSQL in and of itself doesn't allow you to do what you want it to do, you can write a wee short C library and hook that library into the operating system and call a function in that library to do whatever you need it to do. They're called external procedures, essentially. Now, how that works is the Oracle process connects back to the TNS listener and says to the TNS listener, please load this library and execute this function for me. But the TNS listener says, well, I won't do it for you, but what I will do is launch another program called xproc for you, and you speak to xproc from here on in. So xproc is launched, and the Oracle process then starts communicating with xproc. And it says to xproc, please load this library and execute this function, passing it these parameters. And all going well, xproc will load the library, execute the function, and take the parameters. Now, in early versions of Oracle, essentially what we could do is tell, from within the database server, load msvcrt.dll or libc and execute the system function and run this operating system command. But if you look at what's going on underneath the covers, as I said, this whole communication process, it can take place over TCP. So what we can do as an attacker is connect to the TNS listener from over the other side of the network, or even the internet, and say, I'm the Oracle process, wink, wink, nudge, nudge, and say, load this library for me. And the TNS listener will turn around and say, because there's no authentication going on here, it will say, well, I'll tell you what, I won't do it, but I'll get xproc to do it for you. And it will pass us back a TCP port, which we can then connect to and then speak to the xproc process and say, could you do me a favor, load this library for me and execute this function? Xproc goes, yeah, no worries. And off it goes and does it for us. Now, Oracle went ahead and fixed that because obviously, without a user ID and password, someone could compromise the database server. So they fixed it by limiting where you could launch libraries from. So if you attempted to load a library from, say, C:\Windows \System 32, that wouldn't work anymore. And they would log any attempt to attempt to load a library outside of the Oracle home. Now, they did that using a call to sprintf, which is a C function, and the fixed size buffer on the stack. So anyone who can program in C understands where this is going. So we would load a library with an extremely long name, and when that is logged, that would cause a stack-based buffer overflow due to the unsafe call to sprintf. So even then, we could still gain access without a user ID and password by exploiting this buffer overflow in xproc now. And so Oracle went ahead and fixed that, and they did a length check on the name of the library that was being loaded. And if it was over, say, 255 characters, they would not log it, which sounds like a safe thing. But what they failed to do was, when it comes to parsing Oracle environment variables, they did it after the length check. So if we stuck in their $path, what would happen is it would do the length check, and then path would be expanded after the length check, and again, we could put a number of $paths in their $paths and then our computer code and exploit this buffer overflow again. And yeah, so their third fix, wasn't sufficient either. And there's a whole catalog of this going on further. And indeed today, if you're local to the machine, you can still do this. You can still load xproc locally. They've rejected it from across the network now. And, but if you're still local to the machine, you can still trick xproc into executing a function for you. Now, on Windows, it still runs a system, whereas on Unix or Linux-based variants, it should be running as nobody. But if it's not been configured properly, it still might run as the Oracle user. So there are indeed issues where attackers can exploit Oracle without a username and password to gain full access. Moving on, there's typical account compromise. Oracle is renowned for having default usernames and passwords. System, in older versions particularly, this was bad. So System had a password of manager, Sys had a password of change on install, DBNSMP had a password of DBNSMP, CTXSys had a password of CTXSys, and there's about 600 different accounts, depending upon which applications are installed, that have a default username and password. So a wily attacker, or even a not-so-wily attacker, would just fire off the list of default usernames and passwords and trivially gain access. But of course, in 10G, Oracle changed that to now have the password set during the install process, and for the system, the sysman, the sys, and the DBNSMP accounts. But one of the fun facts is the default passwords are still in place during the install procedure. So as long as you know an Oracle database is being installed, you can connect to sys with the password of change and install during the install process and do your nefarious stuff at that particular time. And of course, there's other things as well. The passwords that's chosen is stored in log files on the database server where the database has been installed. So if you can gain file access to that database server, you can snarf these files and decrypt the passwords from them because, there's a well-known published key now, and you can get these passwords straight out again. So there have definitely been issues even here moving forwards. And of course, in web-based applications, the authentication is all handled for you by the web application. So you just piggyback your SQL off the top of that, so you can gain access that way, of course. So gaining access is a trivial thing. Let's talk about the forensics aspect of that now. So remember the TNS listener, it handles all the communication between the remote clients and the database server. So when someone connects to the Oracle database server, their first port of call is the TNS listener. And for every connection that's made, the TNS listener logs an entry for us. So let's have a look. Okay. Can everybody see that at the back, or shall I increase the font size? Sorry. Increase. Okay, thanks. Okay, so what we have in here basically is a number of connections. Okay, here we go. This here is if I highlight in here, it goes on. Actually, let me change the window size, properties, layout, 102. Okay, Control C. Screen buff size. That should be working fine. CLS. Oh, I see. Right, properties. 80. Okay. Right. Okay, so when a connection is made to the Oracle listener, the program that's making the connection sends certain bits of information about itself. So we can see here the program itself is sending its name, sqlplus.exe. It's attempting to connect to the service ORCL, and so on. And for every connection that's made by a proper Oracle client, a new connection is made. So what happens is the client connects to the listener, says, please provide me access to this service. If the service is known, the Oracle, the TNS listener will pass you off to the Oracle process. It will say, it's listening on this port, and the client will then connect to that port and so on. Now, that's what a typical normal Oracle client does. Now, if authentication fails for whatever reason, the connection is torn down, and the user has to go through the same process, reconnecting to the listener. The listener then, hands you off to the Oracle process. You then connect to the Oracle process. And this takes time if you're going to be brute forcing a user ID and password, for example, because you have to make a new connection every single time and so on. However, after a bit of research a few years ago, I found out that we could use the existing connection to the Oracle process. If it told us, no, the username and password is wrong, it was the client's responsibility to tear down that connection. So if we choose not to, we don't have to tear that connection down. And so we can just keep on firing down the same TCP pipe, multiple connection attempts. So you can see here, this entry here is for a single connection. If I do it multiple times, you'll see there's let me actually do this instead. sys/password at ORCL. Okay, so you can see there's a connection there and a log entry for each connection. However, using a tool I wrote earlier, we don't actually need to connect every single time. As I said, we can keep on firing connection requests down that pipe. And I just need the right command prompt window. Actually, I'll tell you what, let's keep this one open. cd/tools, cd oak. Let me close that up a bit so you can see it better. Okay. Oak is just a toolkit I wrote a few years ago. Stands for the Oracle Assessment Kit. And there's a bunch of tools in there. And one of them is pwd brute. Basically, it takes the host, the port, the SID. The SID basically is the service identifier, the username, and the password file. So this tool was written in 2007, and it still works today against even the latest version of the product. Now, the host is 127.0.0.1. Port is 1521. SID is ORCL. We're going to brute force the sys account. Oracle 11G release 2, and earlier, 10G and so on, everything. Sorry, start again. Oracle 11, whether it's release 1 or 2 and so on, will lock accounts now if you attempt to brute force. Unless it's the sys account, of course, because you can never lock out the sys account. So any attacker will target the sys account. So it's imperative to have an extremely strong password on the sys account. So if I passwords.txt, this is it now connecting and attempting. Now you can see there, sys password must log in as sysdba, password is password, and so on. But if we look at the difference in errors, so if the password is wrong, we'll get this as a response. And if the password is correct, because we're not logging in as a sysdba, we'll get connection should be a sysdba. So we can infer from that the password is correct, which is indeed correct because the password is password. But if we look at the TNS listener log file now, we can see there has only been one connection attempt in there, and the host is JDBC, but that's because I'm telling it it's JDBC. This is my attack tool. Everything that is coming from here, basically, is under the control by the client. So this is not trustworthy. But you can see, basically, even though I've done multiple connection attempts, oops, let's run that again. Pipe it to more. This is me setting up the connection. There's attempt 1, there's attempt 2, and so on. And, excuse me, it goes on until such time that, we crack the password. But again, we'll see, there's only one connection attempt, and that's it there. So it's just something, one of the gotchas in terms of a forensic investigation to be aware of, that when someone's brute forcing or attempting to brute force an Oracle username and password, don't just look for multiple entries all within like a given second. Like there were suddenly 50 connection attempts within the same second, all from the same host. So that must be, which it probably will be if there's all these connection attempts. It's indicative of a brute forcing attempt. However, there might be brute forcing attempts that aren't actually logged because there's only one connection and so on. It's just one of those gotchas. And obviously, if someone's coming in through SQL injection, there isn't going to be anything in the TNS listener other than, excuse me, other than obviously the connection attempt that's made by the application and so on. So whether they've gained access using a username and password or without a username and password, let's just assume now the attacker has gained access. So they want to elevate their privileges from a lowly user account to a highly privileged account. So let's do that. Connect Scott / actually, let's create an account. Create user BH 2011 identified by password. Grant create session to BH 2011. Okay, connect. Actually, before we do that, grant execute on vuln proc to public. Connect BH 2011 with a password of password at ORCL. Okay, so we're connected to the Oracle database server as the user BH 2011. If we do select star from session privs, we should see we only have the create session privilege. Now, thanks very much. What that means is we are the lowliest of the low as far as this user is concerned. Now, Oracle has a whole bunch of objects inside it known as PL SQL packages, procedures, functions, and so on. Over the years, there have been hundreds, literally hundreds, maybe 300 to 400 PL SQL injection issues that allow a low-privileged user like this BH 2011 account that we've created to gain sys privileges just through PL SQL injection alone. Now, the reason this works is because PL SQL objects are created by default with definer rights privileges. There is an additional execution model called auth ID privileges, basically where it's the user account that's executing the process. Invoker privileges, that's the word I was looking for. So if the invoker, if an object has invoker rights privileges, it takes the privileges of the user who's invoking the function or procedure or whatever it happens to be. But by default, they're definer rights. So if sys defines a procedure or function or whatever that's vulnerable to PL SQL injection, then any executed code, any injected code will execute with the privileges of the sys user and not the user that's executing the function. So here we have a procedure I made earlier called vulnproc. Exec sys doesn't do very much. I'll show you the code for it in a second. Foo. So all it does basically is it takes a parameter. Let's show you the code. Should have the code somewhere. Okay, there's the code for the procedure. Can everybody see that at the back? Nope. That's what you get for sitting at the back then. Font, here we go. Cancel, Control A, format, font. 60. Is that better? Yeah? Okay, so the code basically takes user input str and embeds that, concatenates it into a SQL query select object name from all objects where owner equals user input and executes that query. Doesn't do very much. It's simply for demonstration purposes only. But as I said, there are about over the lifetime of Oracle, there's been about 300 to 400 real-world instances of this. So let's show you what can be done with this. Okay. So to prove that it's vulnerable to SQL injection, if I just put the double quotes in, we'll see we'll get SQL command not properly terminated. That's indicative that there's SQL injection going on here. So if I then go minus minus, that should fix it. Again, indicative that SQL injection is working. If I then go pipe user bracket like this, now that should have worked. Or didn't it? I'm sorry? No, I think I had them in there. We don't need it anyway. It was just for demo purposes. Right, let's go back to here. Let's go to one I made earlier. Okay, so what we're going to do is insert this, okay? So there is a limitation on executing additional SQL when it comes to Oracle. In Microsoft SQL Server, you can batch queries. You can just add as many select statements as you want and bang them on one after the other. And indeed, it doesn't have to be a select statement. You can do inserts and so on till the cows come home. But you can't batch SQL statements with Oracle. And if you are within the middle of a select statement, then the best thing you can do without any additional hacking is another select statement. If you're in a DML statement, a DML is data manipulation language, so things like insert, delete, and update, and so on, we can additionally do inserts, deletes, and updates because there's transactions taking place now. So we need a way to hack additionally the situation where we're injecting into a select statement to execute arbitrary SQL, anything we want, basically. So we can inject an auxiliary inject function, and what I mean by that is a helper function that allows us to do whatever we want to do. Now, prior to Oracle fixing it, I wrote a paper on injecting cursors that we could then execute via dbms SQL.execute. So we would set up our nefarious SQL, for example, grant DBA to public, parse that statement and create a cursor, which we would then pass to the vulnerable procedure and pass it via the dbms SQL.execute function, which would then be executed by the higher privilege process procedure, it's sys in this case, and execute our cursor, which is like grant DBA and so on. But Oracle fixed that to prevent cursor injection attacks. So we have to look for other methods now, and so any function that's extant on the system that allows us to execute arbitrary SQL is a winner for us, okay? Now there's one called dbms XML query, that's the name of the package, and the function is new context. Now what new context does is takes an arbitrary SQL query and executes it simply. It should be a select statement, for creating XML documents and so on, but you can execute anonymous blocks of PLSQL as well. So what we're going to do is a little trick. So declare pragma autonomous transaction essentially tells the PL/SQL compiler that what we're doing is a discrete unit in and of itself, and you can go ahead and execute it without any qualms whatsoever. Now, if we didn't have this in there, we would get an error coming back saying DML are not allowed within a select query, essentially. So this basically is to trick the PL/SQL compiler into executing this for us. And what we're going to do is execute immediate grant DBA to public. Now, we shouldn't have that privilege already, so if I go set role DBA, we've not been granted that role, or it doesn't exist. Of course, the role exists, but as far as the user is concerned, because they've not been given the role, they can't see the role, okay? So now they're going to take care of that and actually inject into, sorry, I need to put sys in front of that, inject into this vulnerable procedure and execute the grant DBA to public DDL. DDL is data definition language and includes things like create, grant, drop, and so on. So that's just churning away. Okay, so it says it's succeeded. So if I go now set role DBA, it's role set. Now if I do, again, select star from session privileges, I have every single privilege. Session privs. So we've gone from simply create session privileges, injected into a vulnerable procedure, the grant DBA SQL statement, set the role, and now we've got every single privilege we need. And as I said, this isn't like, whilst I'm using a homemade example, Oracle have been patching this with every single critical patch update. They're patching flaws like this. I just didn't want to use a real-world one. Okay, so we can see elevating privileges is trivial. If we did, like we've done there, grant DBA, that executes what's known as a DDL statement, which I mentioned previously. Now, DDL can be found in the redo log files trivially, okay, because it stands out like a sore thumb. We'll see this later on. One of the tools I've written basically allows us to go through the redo log files, which is where all the transaction information is taken from, is stored basically, and DDL jumps straight out at you, even if you're just using grep, which is anathema as far as I'm concerned. So what an attacker might do is choose to insert directly into the sysauth table, which is where all information about the privileges are stored. So just because there isn't a grant DBA to public kind of statement in the DDL, someone may have still granted permissions to DBA privileges to the public user, or any user for that matter, using a direct insert into sysauth. So we have to, as a forensic investigator, look at these key tables like sysauth, obj, user, dollar, and so on to make sure there's been no hanky-panky taking place under the covers without using DDL. Okay. How are we doing for time? Plenty. Okay. Breaking out of the database. And again, we'll come back to the redo logs and start mining them for information in a minute, but I want to continue with the compromise stuff first. Okay, so they've elevated their privileges. They can now do whatever they want to the database server. They might choose to run operating system commands. Or they might choose to change the sys password and connect to the database as the sys user. And if they do so, they can then use auradebug. Auradebug has been well documented in the past, and it has a couple of it allows someone with the requisite privileges, in other words, sysdba privileges, to start manipulating memory using peek and poke. And there's other cool stuff in there. For example, there's a call function that allows us to call arbitrary functions. So what we can do is build structures in memory, or even just simply strings, and using poke, which allows us to write to arbitrary memory addresses, and we'll see this happening in a minute, and then call functions and pass the addresses of our structures in memory and so on, and do whatever we want, as if we were executing arbitrary code. So let's do this because it's quite fun. It's quite a simple one. If I connect. So let's say, remember I've now got I've got all these privileges as the lowly user. So I'm now going to go alter user sys identified by BH 2011. Okay, so I've now just changed the sys password of the sys user to BH 2011. So I can then connect as sys/BH 2011 at ORCL as sysdba. Okay, so I'm now connected as the sys user, which allows me to use this auradebug functionality. So let's do that. Okay. So first off, I set the process ID. I want to debug, essentially, to my own process ID, set my PID. And now what I'm going to do is start writing into memory. So let me increase the font size so you can see it at the back. Font 16. Okay. Can you guys see that at the back? Okay. Great. Thanks. Okay. So the memory address I'm choosing, I was hacking it around earlier, so rather than wasting time I've got some nice addresses for us. Okay, so what I'm going to do is execute the net user orahack pwd/add operating system command. In other words, I'm going to create an operating system user. Now, this works obviously because under Windows, Oracle runs as local system, so any operating system command that Oracle executes will execute with system privileges. Now, so what I'm going to do is write to this memory address the net space of the net command, and then incrementing the address by 4, I'm then going to write another 4 bytes until I've written in memory entirely net user orahack pwd/add. So if I start doing this, okay, so I've now written into memory that address, that net stuff. Where are we going? And now what I'm going to do is call the system function. And in C, the system function takes the address of a string we want to execute. And that obviously can be found in memory at this address because we've just written our net user add command to it there. So if I then execute that, actually before we do that, if I do host net user, we'll see that, actually let me delete that one, net host, because we'll come back to that net user or a hack 2 /delete. Okay, so if we look at the users, there's the VMware user, the administrator David and guest and so on. When I execute this, it will call the system function, going to that memory address and taking that net user orahack password/add command. Okay, function returns 0. So if I now look at the users, we can see that orahack exists. Okay, so imagine I've done this remotely from across the other side of the internet by writing into memory using oradebug poke commands and calling the name of functions. We can execute arbitrary code. It doesn't have to be the system function. We could, for example, use this to create a reverse shell and connect back to us and so on. You can do anything you want, essentially. There is no limitation. Okay, so one of the good things about, well, one of the bad things about oradebug is obviously you can do this kind of stuff. One of the good things about it is every time you use it, it's logged. So if we connect, oops, what happened there? cd, okay, dir, find str /m/i/s/c or debug. Actually, we don't need the s because we don't need all those directories. Okay, so if I look in this one here, this trace file basically contains every single time we execute anything on the oradebug, this trace file is created. So we can see the setpid command. We've written poke, and we can, as a forensic investigator, gain access to this file, obviously, as part of the investigation, and then reverse engineer what they've done, because we can see what they've written in memory. So we can decompile this, essentially, and see that they've executed the net user or a hack, pwd/add command, and at the very bottom, they've executed that function they've executed the system function and passing it that address. So we know exactly what they've done. They've called the system function and added a user. So this is very, very useful, these trace files. Now, obviously, an attacker can go ahead and delete that if they've got all these wonderful privileges anyway. But if they don't delete it, then it's a wonderful source of information. Okay. Now, another one they can do is obviously, remember earlier I spoke about external procedures and calling msvcrt.dll and calling the system function on that. Another way of doing that is obviously by using the legitimate aspect of the database that does all this. So if we open this one, not that one. Okay. I'm going to do the one that's going to fail first because I'm going to show you some useful forensic information. Let's get rid of that. Control-C. Right. So we've created a library called libsysexec. That's a library as far as the Oracle database server is concerned, and it links to msvcrt.dll, or it's going to, on the operating system. And once we've done that, we can then wrap that library inside a procedure. You can see here, we're creating a procedure called plsysexec, takes a command string, and we pass that command string to the system function in the library we've created called libsysexec, okay? And then when we execute that, in this instance, we're going to get an error message. It's going to complain that it's an invalid DLL path. Because remember I told you earlier that this was easy to abuse, so Oracle fixed it by restricting what DLLs could be loaded by putting them in the Oracle, making sure they're in the Oracle home directory. Well, that's what happens, and there's a log file that's created. Where did it go? Tell you what, do it here. Redo it. Why is that not working? File. Procmon. Right, here, jump to, we can see the log file is created where an attempt is made to execute a function inside a library that exists outside of the Oracle home directory. So we can see here, request originating from external function, blah-de-blah, and so on. And, so we've got some nice, useful information in there. However, one of the recent issues with the most, sorry, let's start again. Oracle 11g release 2 on Windows, for some reason, sticks msvcrt.dll into the Oracle home bin directory. So whilst you previously couldn't exploit this flaw anymore because Oracle had restricted you to DLLs in the Oracle home directory, by putting msvcrt.dll into the bin directory, you can suddenly start executing system commands again. It defies explanation. So all the attacker needs to do now, and this is the latest version of Oracle, fully patched, we just provide Oracle home bin /msvcrt.dll. So if we do this now, library created, create that again, just so it's all good. And this time, when we execute the function, it's going to succeed. There's no invalid DLL path because we're in the right area. We're in the Oracle home. We're in the bin directory in the Oracle home. So if we now look at the host net user command, we can see that orahack2 is back in there. We did it earlier because it was just simply there from previous. I mean, we can do it. Add a third, just to show 3 or 4, whatever. So net user, we've now got orahack4 and so on. So we're now running operating system commands back through msvcrt.dll because for some reason Oracle thought it was a wise thing to do to dump it in the bin directory in the Oracle home. Security decisions taken at that company mystify me. Okay. Where are we up to? So many windows open. Here we go. Okay, so there's various ways of running operating system commands. We've had a good look at a few of them. Okay, so we'll move on to the second half of the presentation. We've got 25 minutes left, so I'll try and get it all fitted in. So where's the evidence? Okay. Evidence is everywhere in Oracle. That's one of the best things Oracle have done, is there's so much redundancy built into it as a database server. there's a wealth of information about what's taken place as far as activities in the database is concerned. SQL Server, it's a nice database server, pretty lightweight, very, very, very secure. I have to say very, very secure because it is indeed very, very secure. It's had SQL Server 2008, I think 0 patches required, security patches, critical patches. SQL Server 2005, 6-year-old product, I think 3 patches, secure, critical patches required. When you look at Oracle, in contrast, there's about 10 to 15 critical patches that are patched every 3 months. So just in terms of the stark difference in their security posture, there's a world of difference. But as far as redundancy is concerned, Oracle is light years ahead of Microsoft SQL Server. And as a consequence, there's all this beautiful, juicy information available to a forensics investigator. So the system, metadata itself, is a wonderful source. The data dictionary is the information that makes up the database server itself. The data files, the data itself is obviously forensic, or forensic value. Deleted and updated data is left behind. So when I update a particular row in a database server, the row isn't scrubbed or overwritten with the new information. It's sort of marked as deleted and a new row is created. So the old information is still there. And the same with deleted information. It's just marked as deleted. Each row of information has a row header, and the first bit of that row header, 3-byte row header, the 5th bit of that first byte, essentially, if you flip it, it says it's deleted. If you flip it again, it says it's not deleted. And that's how you can work out if data has been deleted or not. So even though when you do a select query on a particular table and there's no data in there, there might still be data. It's just been deleted, and we just look directly in the data file. Look at that 5th bit of the first byte of the row header. Active session history is a wonderful source of information. So if someone's trying to exfiltrate data, and let's say there's 1 million records, and they're using something like UTL HTTP or UTL Integer to exfiltrate data in an out-of-band fashion over the network, that will take a long time. In fact, just selecting 1 million records will take a long time. Now, what happens in the background, there is this thing called active session history, where every 3 seconds, Oracle polls the system to find out what's going on in the database at that particular time. Now, as a consequence, if an SQL query takes 3 seconds or more, there's going to be a snapshot in memory of this active session history, essentially. And what happens later on is the stuff in memory is sampled, and approximately 1 in 10 of these entries in memory will be written permanently on disk into one of the data files as the active session history log, essentially. So if a query takes, say, 30 seconds or longer, then there's going to be enough stamps in there, 10 stamps for one particular query over 30 seconds, because it's taking a poll every 3 seconds, remember. So there's a very high chance that one of these is going to end up, one of these snapshots is going to end up in the fixed, logged active session history. And of course, if a query takes 3 minutes because they're exfiltrating data over the network using UTL HTTP or something, then there's going to be, multiple stamps in the active session history. So that's a wonderful source of information for working out whether someone's trying to exfiltrate data. The transaction logs, the redo logs themselves, are again wonderful source. Every time you update or delete or do select for updates or whatever it happens to be, anything that requires a transaction will be in these redo logs. The undo segments, again, wonderful source of information. The memory itself. If you're doing a live response, one of the best sources of forensic information is, of course, the memory. Dumping certain virtual tables, VSQL has a list of about 3,000 to 5,000 of the previously executed SQL queries. So if you catch a compromise in action as it's taking place, you can snarf from memory what actions the attacker is taking. The $DB object cache is another wonderful source of information. There are certain database objects which are associated with vulnerability. So, for example, there's an Oracle class called UTL wrapper. Okay, and this wrapper is undocumented, it's never been used, there's no bit of code, rather, from within the database server that uses this UTL wrapper. And so if it's been used, it gets put in this DB object cache. And the only time you would ever use it, what it does essentially, it allows an attacker to execute operating system commands provided they have the requisite Java privileges. In fact, about 2 years ago, I published a paper on gaining the requisite Java privileges by exploiting a flaw that then allowed us to execute this UTL wrapper and so on. So it was a nice little attack. But if it's in this DB object cache, if this object is in memory, then the only reason it's in memory is because someone's attacked you, because no one else uses this stuff. So looking in this DB object cache, we can very quickly ascertain whether certain nefarious activity has been taking place. We looked at the TNS log files earlier. You know, the information in there is under the control of the attacker to a certain extent, so caveat emptor on that one. And the trace files we saw, like using Aura debug, you know, everything was being logged in there. Any kind of crash or memory corruption or failure when executing Java, that will go in the trace files as well. So the trace files are a wonderful source of information too. So given that we have all this wonderful information, how do we get access to it? Well, it's all proprietary, binary in nature, and it's all undocumented. So I've spent the past few years documenting, well, reverse engineering and documenting all of these structures. And the vendors don't provide tools for forensic investigation, simply because they don't want to admit that their databases could be compromised. So if there are tools that can be co-opted into a forensics investigation, they've not been designed with forensics in mind, remember. So they may change evidence, which is obviously a big no-no, and they don't get everything. You know, so for example, the redo logs can be mined using LogMiner in Oracle, but what happens is in the Oracle redo logs, older logs are overwritten essentially. So older entries, if a log is refreshed and new entries are started written to the top, all the older entries are ignored basically because they're, you know, considered from previous you know, sessions, so to speak. And so the log miner doesn't gain access to that stuff, whereas if we write our own tools, we can gain access to that information. So as a consequence, it's for the past few years, full-on DB breach investigations have been difficult to do because the files are undocumented, and there have been no tools until now, of course. So this is what I've done, and I'll speed through this. So the product is called Verity. It's free, and it provides case management, evidence collation, searching, sorting, filtering, and all the way through to the reporting side of things. And currently, it's stuck together with bubble gum and sellotape. It's still a work in progress, but I've got enough of it working. Certainly the engine is there, the stuff that processes the evidence is all there, and the filtering, I've got some nice GUI stuff, you know, but as I said, it sort of just needs to be linked together properly. So let's start looking at that. Okay, I'm going to stop the database first. So we've just compromised this database server, and this is what we're going to do the investigation on. How are we doing for time? I'm short. Quit. Okay. So this dump action tool basically will take an action. For example, we want to dump DDL. We'll dump the DDL. It takes the name of the redo log file, David /or data /Oracle redo log, and we're going to dump the DDL. Okay. So all this does basically is makes a nice little XML file for us and dumps all of the DDL that can be found in that redo log file. So if we look here, let's CLS this. Let's do that again. Okay, so this particular redo log file, on the 4th of the 8th, that's British. I'm British. So that's not the, that's the 4th of August, 2011, at 23:28, which is, this was when it happened and everything. Let's actually move down to something which happened a few minutes ago. So here we remember when we created that library. That was at 133 essentially. So we can see there the create library, lib sysexec, and so on. So anything that is DDL in nature will be logged. Let's see if we can find the password change. Auto user sys identified by values. That's when the BH user changed the password. The session user is BH 2011. The offset at which this DDL entry can be found is that, and so on. Now, if we look here, let's do some more. Let's actually redirect it to ccolon / 1.ddl, and then let's change that to 2.ddl, and then 3.ddl. So I'm dumping the 3 redo logs, and then there's a nice little tool. Okay, redo logs, file, open files, ccolon /. Let's open these 3. Open. And once we've done this, we can start running like some filtering. So where the session user can matches, say, BH 2011, click on find. So it basically will go through all the DDL output, looking for things that we tell it to do. So for example, in 1.ddl, the session user was BH 2011. At that time, he executed the auto user sys identified by values and so on. Now, Oracle doesn't log the password. Obviously, that would be a security flaw. If someone changed their password and it was found in there. If we didn't want to find anything that does not match that, then anything that doesn't match it, we can start dumping out and everything. So we get a nice list of all the DDL that was ever executed. Now, imagine a database server that has 600 redo logs that have been archived. We can basically, process them all with one fell swoop, and then filter them with this basically. And it can cut the investigation time down dramatically. So 1, we've got the tool to dump the information out, and 2, we've now got the tool to start filtering it in a very easy and quick fashion. And then we can start exporting the information or copying. We've not copied anything. Copy that, export, and so on. And we can clear. So this is a nice little tool. Again, halfway through development and so on. We can start running nice little things off there. Sorry, I'm just really aware of the time. So I'm just going to jump ahead. So we can do that, obviously, for, we can dump insert information, we can dump update information, delete information, DDL and everything like that. So any kind of thing that required a database transaction, we can gain access to trivially. This here is the management side. So basically, we can, add new things, add a redo log file. Let's go ccolon / /David, blah, 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 or data RCL. So add that one, open, okay. And once we've added that, we can then process it, process the redo log file, process and complete, and then we get all that information out. So let's say we we have something that is nefarious. All of this is nefarious activity, of course, but let's say there was only one thing that we're particularly interested in. That one there, create item of interest. Okay, actually, let's do that one instead. Add on create item of interest. This could cause an exception because I was messing around with it earlier. Yes, it did. Nice. Okay, here's one I made earlier. Do you want to stop debugging? Yes, please. Verity. Should never demo beta code. Done. Okay, so let's just... So assuming we've added items of interest, it appears over here. These are things that took place, like grant DBA to public and so on. Once we've got items that we're interested in, we can then click on here, and a nice little report is created for us, which we can modify and so on. And if we don't particularly like an investigation, we can go ahead and delete it. Sure you want to delete. So there's the whole management side and everything like that. But I think the key side is the actual processing of the log files, the data files themselves, to extract the information in a humanly understandable, nice XML format, basically, which we can then use in other tools because it's XML, and as long as you understand the schemas and everything, and we're all good. So we've only got a couple minutes left, so I know that was an extremely quick demo. I'm not going to bore you with it, but any questions about this talk, let's open up to the floor. Any questions at all? So I've explained everything fully and everyone understands 100%? Great. Yep, okay, there's a question over here. Right now, yeah, what happens is you gather the evidence in a forensically sound manner, like taking logs, checksums, like SHA-1 and everything like that, and take it to your workstation and process the evidence on your workstation. The tool needs to be run locally right now. Any other questions? Sure. Well, the offline one basically is no longer being written to, and yeah, they're essentially archived. Yes, so the online one sometimes has stuff at the back of it that is currently being overwritten. So yes, there is extra stuff in there, but there's no additional in the regard of it. It's all the same information, like it's update information, delete information, and so on, but it's no longer accessible by the Oracle utilities anymore because it's considered as slack space and being overwritten. So yeah, there's still stuff recoverable in there, and absolutely, the tools allow you to specify here's where the old stuff can be found, and you point it at it, and it will dump that older information for you. Sure. Any other? Sure. No, because we can dump if we have the system table space, I've written a tool that dumps any data from an Oracle data file. So what we do is any object ID, any block that has an object ID of 18, which is the obj dollar table, we can dump all that information out and get the object ID and object names and so on. Once we've got that, we can then start, when it comes to the inserts that are in the redo log files, the name of the object being inserted into is not in there. The object ID is, okay? So, exactly, yeah. But we can get all this information simply as long the only bit of information we need to know is the object ID of the obj dollar table. Once we have that, everything else we can work out from there. And on most Oracle systems, it's 18. And if on a particular version it's not 18, we just need to look up on the internet what's the object ID of the obj dollar table, kind of. And then again, everything spreads out from there. Sure, there's a question there. No, so the question was, is there a difference between the file formats in Oracle versus Linux? They're exactly the same. Even big endian versus small endian, exactly the same. So yeah, there's no differences there. Question there? Was the question, can you find evidence of a perpetrator cleaning up after an attack? Yes, absolutely. So one of the great things is because there's so much logging taking place, when you attempt to delete something, there's evidence of that delete. So if you're, for example, let's say you're trying to remove entries in the audit table, AUD$, you're going to delete stuff. That's going to be in the redo log in and of itself. If you're then deleting files off the file system, you're going to need a mechanism in which to do that, which requires the creation of an object, for example, a Java object that allows you to shout out to the operating system. But in doing so, you're going to find evidence of that as well. And if you then remove those objects, there's going to be evidence of that as well. So it's really, really difficult to fully hide your tracks. And the amount of noise that actually creates, a DBA is going to notice, or hopefully going to notice something going wrong. Can someone entirely remove their tracks? Absolutely. But it is very, very, very difficult. And there's going to be, the absence of information is going to be evidence in and of itself, if you see what I'm saying. This is a good question, though. Sure? I am. I started with Oracle because it's the hard one to do. The other databases are, trivial because, yeah, their file formats are much easier, basically. So when I get the Oracle one finished, I will do SQL Server, Microsoft SQL Server next. Then I'll end up doing MySQL, and I'll see how it goes. I might get bored of it all and go diving or something again. Sure. Hey, Ryan, how you doing? Yeah, so this will work for Oracle 10G up to the present versions. Oracle 9 is slightly different, but I've got code to do that as well, and Oracle 8 as well. So the code I have works from Oracle 8 to 11, but there are differences between 8 and 9 and 10 and 11, so to speak. So there are differences, but I've accounted for those differences as well. Okay, no more questions I'm seeing. So, well, thank you very much for coming, I hope.